In this video, we'll be examining the relationship between engine displacement and city MPG for a sample of vehicles made in 2015. We'll be using a free online program called CODAP to do the analysis. Engine displacement is essentially the sum of the volume in all the cylinders of an engine. This is measured in liters. Different engines have different number of cylinders. City MPG is the average miles per gallon for city driving. To begin with, we could graph these variables. Basically, each type of engine creates limitations on the range of city MPG for a vehicle. So engine displacement is going to be our independent variable, and it goes on the x-axis. City MPG is the value we want to predict. It goes on our y-axis. If you look at our graph, we notice that there seems to be a negative relationship between engine displacement and city MPG. Low volumes of engine displacement correspond to higher values of city MPG. High values of engine displacement correspond to lower values for city MPG. We could ask the program to find an equation that models the linear relationship that we think exists in this data. This is a least squares line. The program gives us an equation. City MPG, which is our y variable, equals negative 3.24 times engine displacement, which is our x variable, plus 31. Our slope of our equation is negative 3.24. This matches what we thought about the relationship in this data, that there is a negative relationship. The program also gives us an r squared. R squared value is 0.55. R squared is the coefficient of determination. This tells us that 55% of the differences in the city MPG for these vehicles can be explained by this linear relationship. An r squared close to 1 would indicate a strong linear relationship, and 0 would mean no linear relationship. At 55%, our data tends to have a linear relationship. It's not great, but it does exist. But you notice these points far off our equation. This equation does not do a good job of predicting the city MPG for these values. If we go back into our table, we could try to find another variable that might help explain these differences. We'll try transmission type. We'll put it in the center of the graph, and the program has now separated the data into manual transmission cars and automatic transmission. All the purple dots represent the manual transmission vehicles. The purple line is a least squares line for the manual transmission vehicles. We also get an equation for this purple line. You notice the points that we were concerned about, they're all automatic transmission cars. The two lines we have, the yellow one for automatic transmission and the purple one for manual transmission, they seem to be very similar. They both have a negative slope, their y-intercepts are close together. I'd say that transmission type did not offer much insight into the behavior between engine displacement and city MPG, and it didn't really explain the behavior of these points up here. We could take transmission type off of our graph and just try to explore the nature of this linear relationship some more. We could ask the program to provide a graphic of the squares of the residuals. A residual is a difference between the actual value for city MPG and the value predicted by the least squares line. When we choose this option, we get a graphic. These tightly packed squares indicate those places where our equation made a good prediction for city MPG. These large squares represent the places where our equation did not do such a good job predicting city MPG. When one calculates a least squares line, we're trying to minimize the sum of all these squares. We can create a new category. I called residual for city MPG, and we could ask the program to calculate the residuals for all of our data. Our x variable is engine displacement. Our y variable is city MPG. And that is all we need. And the program has now calculated the residual values for all of our data. Notice some of the points are close to 0. This indicates places where our equation did a good job of predicting the city MPG. Some of the data points are very high positive. These are places where our equation predicted a value that was lower than the actual value. Some of these are very low negative values. These are places where our equation predicted a value for city MPG that was higher than the actual value. We can create another graph, and we could put our residuals against engine displacement on the second graph. Engine displacement is still our x variable. Our residuals is our y variable. And we now have a residual graph. When looking at this residual plot, we want to see the residuals randomly distributed above and below this 0 line. This 0 line is where our equation accurately predicted city MPG, and these residuals are very close to 0. You want the data to be evenly dispersed and for there to be no discernible pattern. They seem fairly evenly dispersed, not terrific. We still have all these points up here, and we have some points down here. If you click on the points, you could see the corresponding point in our original graph. As expected, the points up here in our residual graph correspond to the points up here in our original graph. Based on our R-squared value and looking at the residual plot, there seems to be a linear relationship between engine displacement and city MPG. It's not a very strong relationship, but it does seem to have a negative relationship. It would be worthwhile to go back into this data set and try to find another variable that might explain these points that are way off of our equation.